Where you see it? Inside or outside?
Inside.
Okay. Does it sound outside?
I never see him.
Did you talk to him?
Yeah. He told me he was going
Yeah.
but he didn't know it because today it's your day for me.
Oh, has he not paid you this?
That's what he told me.
So I normally don't do this because it's my colleague Sarah Gofford and Rachel Sullivan at the Macmillan Innovation Studio who really put together this series of workshops for students at the Macmillan Innovation Studio and the Social Innovation Challenge. But this time, I just want to thank Canon Reeves. If you're in my class and you attended that session in particular, Canon came maybe at the second, third, or fourth session to share with you his idea, his experience in the Social Innovation Challenge. But I think highly of Canon. I know that one day we're going to take this idea to countries like India or countries like in any place in sub-Saharan Africa and make it available for kids there. This idea that he has and promote education through his inventions and his creative mind. So I have always thought very highly of Canon. I am very lucky that I got to meet him, and I hope that you appreciate what he has to share with you. So thank you. Thank you.
All right, what's up, everybody? Wait, one second. All right, so I'm Cannon. I guess I've met some of you, not most of you. A little bit about me. I build robots. That's like the easiest way to put it. So I've been doing this for about 6 years now, and I really fell in love with it when I was in high school. And there's just something about the way that it gave you a way to solve problems creatively in a way that's really fun. I'm a very visual person. Robots are very visible, tangible. So I'm a junior studying computer science. I started in Dr. Regilio's social innovation class the fall of my sophomore year, so I guess last year. And I came into it with this idea of well, actually, I didn't mean to take the class. Total accident. I wasn't planning it. One of the best accidents that's ever happened. And I saw the challenges, and none of them really spoke to me, and so I was like, okay, I want to start something that aligns with my interests. And my interests were tech. It had drastically changed the path that I took in my life, and I wanted to make that opportunity available to others. So I tried to start a code school. I am a computer science major, but I really don't like to code that much. I code robots, and I was trying to do a web development school. So eventually, got through to my thick head that I shouldn't start a code school. I should just do something around robots. So in March, we kind of pivoted, and I started this robotics company, More Technologies. So basically, everything that you see here, we teach, but we make it accessible to kids. So this is a really fun, easy way to introduce kids into coding, into CAD, 3D printing, a lot of fun stuff. So this is this kind of thing is what I do for a living at this point, and I really enjoy it. I'm also captain of the NASA Razorbots team. So I did not build this robot alone. I mainly just did some programming on it. But when we go to Mars, the keyword when, we can't bring everything with us. We can't ship concrete into space. That's expensive. So what we need to do is use what is called local resources. So when we go to Mars, we combine it and then turn that into something we can 3D print. Sounds really simple. We're just getting dirt, taking it from one place and putting it in another. That's actually really hard when you think about the Martian environment. So this robot goes out there, and its drum spins, and it collects up the dirt, and then when it comes back and the drum spins the other way, it dumps the dirt out. Really simple, but really effective. It's also got a really cool arm. It's really powerful. I'll probably reference that some as we go through. So, if you fall asleep over the next, however long this lasts, and you take away nothing, take away these three things. something is infinitely better than nothing. So even if you are not confident in what you're creating, it is better than nothing. Like so much better. Even if it is awful, like awful, it's better than nothing by a large degree. And one of the hardest things with making anything at all, is getting started. And just convince yourself, like, okay, I just need to try. I just need to get something, and you can improve from there. Second off, computers are really, really dumb. As a footnote, except when they're not, that's very limited cases. Computers, super dumb. And then third, these slides are research. So, like, I'm not expecting you all to remember this. This is, like, a lot of information. It's like a brain dump. What I intend this to be is to, one, show you that this tech is accessible to you, even if you haven't done it before. And then two, give you a guideline for later on down the road when you decide you want to do these things. If you decide, you can look back at these. And I'll be emailing these to everybody. So, let's talk about the MVP and a terribly pixelated picture. This is a robot that took months of iteration and work to do. And it's missing a lot of, like, you can't really see the key value of what this is. It's really expandable, so think Lego, but for, like, 3D printed stuff and wooden dowels. This is what it started as. It is, like, zip tied together. There's wires everywhere. This is my adorable little sister. I guess you can't really see it. But, yeah, so the first thing you make doesn't have to be great. It just has to be there enough for you to test a concept. And that was enough for us to test a concept. We took that to a lot of meetings and got a lot of interest and good feedback on our idea while we were early on. So think about what's the minimum amount you can do to just test the idea. Okay, so to get to an MVP, there's a simple process that you follow. Identify a problem, make a prototype, and then test and evaluate and iterate. So when it comes to identifying, it all just like starts with an idea. For me, I found that the best things happen by chance and are random, like taking Dr. Helio's class. So like, once you have an idea, you want to research as much as you can. Like, we live in an amazing, amazing time. Like, there has never been a better time to be a human. If you think about, like, where the majority of the jobs were for the majority of the lifespan of humans, it's in agriculture. You live in the first tiny sector of time in which you're probably not a farmer. That's incredible, because that it allows us to specialize in so many amazing things. So, we have the internet. You have access to as much information as you want. Utilize that. And lastly, ask questions. People are better than the internet because, remember, computers are dumb. And people can share insights that you will never find online. All you have to do is talk to them. So if you're looking for somewhere to start, or you're given kind of a vague challenge, look around you for what problems you see. And I encourage you to find something that you're passionate about. The problem I saw was a lack of STEM education. That's something I'm really deeply passionate about, and so that's what I went to solve. Ask people about their problems if you're just really looking for something to do. And then also, don't overthink it. Just go with your gut on this. For research, I would highly suggest writing your problem down. If you can narrow it down to about 2 sentences, it gets really easy to Google at that point, right? So type into Google exactly what you would ask me if you're going to ask about a problem, and I promise you'll get surprisingly good results. And then Google your problem. A lot. It's amazing. So all of the stuff that I do, I did not learn in college, for the most part. Most of this is learned through Google. Most of this, I was like, I want to do this. How do I do this? I Googled it. I messed up. I kept Googling it, and then I found something that works. Like, there's so much information online, you don't really need to go to college in some cases. And then Google your problem more. I know it's a terrible thing to say, we're in a college. Stay in school, kids. I'm a kid too, I don't know why I'm saying that. But yeah, keep Googling, all good stuff. When it comes to asking questions, so start with people who are really close to the problem. So for me, that would be like educators or parents who feel like their kid's not getting enough education. Also talk to people who are already trying to solve it. This is huge and is often overlooked. You are students, you are young. There are very few people that will not talk to you. It sounds kind of weird, but no joke, I've interviewed easily 15 of my closest competitors. And got really valuable stuff that they probably shouldn't have shared with me, but they did because I'm a student, and they just kind of underassumed what I could do. So really, go talk to people who are close to it, and don't be afraid to reach out over email. Again, you're a student, play that, people are nice, they want to help you out, and people are just generally good people. So don't waste their time, but send an email and ask if you can talk to them. Also, I should note, I talk a lot, I ramble a lot. Interrupt me if you have a question, over any of this. So let's start making things. So if you want to make something, there's 3 key steps. Understand what you need to make. truly ties into understanding the problem, understand how you're going to make it, which is often the hardest step, and then just actually doing it. So in understanding what you need to make, there's these nifty things that engineers use called design constraints. It is a way for you to kind of like start to visualize what you need to make. So we're talking design constraints. It's things that are really big picture, right? So if we're building this robot for NASA to send to Mars, it can't have rubber because rubber is going to melt in space. That's a pretty easy design constraint to understand. It has to be lightweight. It can't blow up. Things like this. But it also, on the other side of that, it needs to be able to actually get dirt. It needs to not get stuck on Mars. So, like, think of your thing you're making as a black box. And then think about what are the outcomes of this black box just has to have. Like, if it doesn't do these things, it's not even useful. It's paperweight. So for narrowing this down, I guess I just got to ramble on about that. I would write like 3 to 5 constraints before you start. That's like a good number. Creativity likes constraints in some instances. I think like when you just have everything to do, it's hard to do something. But when you've got a pretty narrow scope, it's easier to start something. And then once you have your constraints, just start sketching things. Like this is super valuable. The whiteboards here and in the rooms, like those are some of your greatest assets because putting your ideas to paper, or in this case whiteboard, lets other people see it, and it also just clears your head and lets you focus on it. So once you've got kind of a general design that you want, after you've generated a few, you've narrowed down what you want, prioritize what it needs to do, like what's the most important. So with this robot, is it most important that it can carry a lot of Martian dirt, or is it most important that it can move really fast to go back and forth between the dirt? And then go with your gut. This is something that will change over time in the way that your gut views things. You will just like get a sense for your design, but trust yourself here. And then speed is key. You don't want to get frozen up because you don't know what the best path is. Again, something infinitely better than nothing. Just choose something and go with it if you need to. Okay, so now we're getting to the tech part. And this is where there's going to be kind of a big brain dump. Interrupt me again if you have any questions. And I should note too, I build robots. Robots involve a lot of different kinds of engineering, but it's not all kinds. And a prototype does not have to be anything engineering related. It could be a policy, it could be a picture, it could be anything. So don't let this constrain what you think a prototype could be. So everything, everything around you does 3 things. That sounds kind of crazy, but it's really true. It's going to sense and take inputs. It's going to think about those inputs, and then it's going to do something with that information. So here's a simple robot that is sensing. It's got a sensor up here that's reading distance. It's thinking about whether or not something's too close and it should turn, and then it's acting and turning around. And in the end, you get kind of a cool paint. Take that step up with an autonomous car. It's sensing, a little more complex sensing, but it's sensing, it's thinking, deciding when can I go, and it's like, oh, there's people in front of me, I can't go. That's its action. Or it's moving and going. And even take that a step further, that's what you're doing like every day, every second. Like, if you're walking somewhere, you like think about your surrounding, you sense it, you think about it, and then you do something. It's just that people are insanely good sensors. Like, the amount of information that's streaming through your eyes and just your body as a whole right now is absolutely insane. People are crazy. Like, if we could make a computer or a robot that's as good as you, even half as good as you would be a trillionaire. No problem, because people are insanely great. Anyway, so sensing. There's a great divide between the digital world we've come to love and the physical world we live in. And that divide is that this is really stupid. And this has no idea what's around it, right? Like, the only thing this can know is the sensors I give it. And that's the only way it can perceive anything around us. Whereas we have sensors that are inherently better, that lets us see around us. So when it comes to sensing, there needs to be something that's like taking in that information, right? So if a tree falls on a wood and nobody's around, is anybody here, or does it make a sound, whatever it is, right? The key there is that, yeah, it's making a sound, but there's nothing to compute the sound and like process it. So same thing with sensors. There needs to be some kind of computer. And fun fact, there are tiny computers everywhere. Not just your phone, not just your laptop, but everywhere. The microwave, the fridge, the Keurig, everything has tiny computers. They are insanely cheap these days, and they're everywhere. So if you're wanting to start There's kind of several layers of computation and things. So at the lowest level, there's the Arduino. Love using the Arduino. It's what our robots use. It can only run one program at a time. So it's super quick and easy to get started with. It's really good for interfacing with things. This comes down to some really detailed electrical engineering things, but it is good at taking things in and putting things out. You can control motors, sensors. There's tons of tutorials out there for this. So if you want to make something do things, this is a good way to start. And it's useful for lower level control. So it's good to control a motor with this, but you probably couldn't use it to scrape people's data on Facebook. So it's not that strong, but it does have some beef to it, and it is useful. I have these things. I don't know why I'm not showing you. Here's an Arduino. You guys can pass this around. And here's a Raspberry Pi. No, you can't eat it. No, I've not tried. It's like your computer, but smaller. I mean, it really is a large version of Linux. It's like a desktop. People have used them for that kind of stuff. It's okay at taking things in, like sensors and motors. It's a bit harder to program it to do that, but it can do it if you want to. And it's useful for high-level programming to a point. So, yeah, you could run servers off it. People do that, but you're going to run into computation power issues. Any questions about any of these? About when you should use it? Good? Okay. So, there's a few things that are easy to sense with the Arduino. Light is a good one of those. There's some sensors that do that pretty easily. Distance to a point, like kind of close distances, and then rotation. There's a lot of sensors to sense rotation. Whereas things it's not good at, people. People are the worst. They're really hard to sense. We're very complex bags of water, and there aren't a lot of sensors that can just easily do that outside of our eyes. Position and location. So this one's kind of weird. You walk into a room and you know very easily where you are. Very easily. Incredibly so. How many of you could walk back to the school right now, without looking at a map? Pretty well, right? You've got this kind of innate spatial awareness where you have an idea of where you are in the physical world, and it's pretty good. Robots are not the same way. This robot's really stupid and doesn't know where it is. It could be on Mars right now and it wouldn't know the difference. And I'm sure you're thinking oh, GPS. Yes, GPS, which is insane how that works, but it's only accurate to a point, and GPS doesn't work indoors. So to localize indoors, which is just how a robot knows where it is, you've got to do some crazy things. So one of the easiest way to do this is to use what's called LiDAR. And that's what you see on all the autonomous cars. So what's happening is you've got a laser. And if I point that laser at something, it's going to bounce back at me. I can time how long that takes, and I can calculate that distance because I know the speed of light, right? So if I turn and I spin around really fast, I know the distance of everything around me on a 2D plane. And in theory, if I do that here, the distances I see are different than if I do that here. And so a robot can take that and build a map of where it is in the world. But it's not always that accurate, and it's you need a lot of computation power. And if you kidnap a robot and just place it somewhere randomly in that room, it won't know where it is, which is kind of crazy. Also, far away things. So the sensors that I mentioned, the ones that we use on our robot, they can't see that far. Inaccuracies build up. There's some really expensive things that can solve this, but for the most part, far away things are hard. So your entire world is in ones and zeros. Everything on your phone, your banking data, your social media, every picture you've ever taken is at some point converted to what is essentially ones and zeros. Kind of a wild concept, but very important because everything that we build has to think in terms of these ones and zeros. So when we talk about sensing people, cameras and computer vision are arguably the best way to do this. And anytime you're taking a picture, that's turning into ones and zeros. So when you think about how hard it is to look at a big thing of ones and zeros in numbers and then figure out if that's a person, that's insane. That's really hard. There's no easy way to do that. And it's taken us a long time to get where we can do it reliably. And we've still got a long ways to go in computer vision. So the way that computer vision vaguely works and what you vaguely need. Let's talk about tools. If you're going to do computer vision, I would suggest using OpenCV. Doesn't matter if you remember this, just come back to this if you need it. And I would recommend using Python 3 and OpenCV 3. useful because they make it where this stuff is easy. Like this is just a tutorial that you can run. I didn't have to do any crazy code for this. It just kind of works. And then also use something called edge computing. So I talked about how the Arduino is dumb, and all computers are dumb, but this one's like super dumb. It can only run one program. It doesn't have a lot of computational power. So what people have come up with, which is super clever, is to make it where the computing and the thinking doesn't happen here, but it happens here on the camera. This is called edge computing. So what's happening is this tiny camera has another tiny computer that's really, really powerful. But all that it's good at is reading in that camera and like sensing things from it. So there are cameras that you can buy, like this one, which is really good at detecting colors. That you can train it on the color orange, red, whatever. Or like there's this one, which is insane, and like this can recognize faces. But what this does is it like, if you imagine this being the camera that's running this image, what it would do is sense my face, and it would say, here's a rectangle, and it would send the information for where a rectangle is and how big it is. And that's not that much data, right? You've got one coordinate right here, and you've got a length and a width. So like 4 numbers, and you've got it. And that's where my face is. And the robot can do things or create actions from that. This is hard. Like, computer vision is really hard for those reasons that I talked about. There have been a lot of advancements using like machine learning and deep learning. And basically, like some of the best ways that we can do this stuff is just to give a computer like a ton of images. Like, for this to be able to recognize my face, it was fed thousands and thousands and thousands of people's faces, like just pictures of faces, and then through software black magic, essentially, it learned to detect certain features that are a face. It's not perfect. There are cases where it doesn't work, a lot of cases where it doesn't work, but that's essentially how we see things. Yeah?
You talked about ones and zeros as being the form under which it understands everything.
Mm-hmm.
So when you feed it all this thousands of pictures, does it learn a code of ones and zeros that describe the face? Is that it?
So it's pretty close. It learns like the differences between the ones and zeros. So when I say ones and zeros, what I mean is it's a color. So every single pixel here is identified by a color. It's a combination of 3 numbers. Each number is 0 to 255. And then those are in binary. And so like what it's looking at is the numbers around it. It is crazy stuff. But it is at the lowest level, it's looking at those ones and zeros, and then just saying this looks like a face, I guess. And it's like it's looking for key features. So like a nose would be a key feature that it identifies, or like eyes. Does that answer? Are there any other questions about this? This is super fascinating stuff. I get super excited about it. Okay, cool. So how does a computer think? What is the process? It is actually surprisingly simple in a way because they're dumb. So most computers, especially the Arduino, they think sequentially. That's kind of like if you turned on Google Maps and it told you step by step what you needed to do, or you read a recipe, right? That's all it is. Arduino is written in C++. This is a pretty quick language to learn, and one of the first languages that I learned. And then it only runs one program, so super quick to get started with the Arduino. And like I said, it runs line by line. So it would just in this case, look at this, then move here, then move here, then move here. And there's things around why it's moving, when it's moving. But anyways, that's all that matters. That's how it works. There's computers that don't work like that, but the ones we use do. So what if I need to talk to things? So I use my phone to talk constantly, right? Like we're always on our phone. But it's actually pretty crazy that we can communicate so effectively. In fact, that spider, I just dropped out of my phone. So I was actually going to do this earlier. I just forgot. I got to make sure. So what's happening here? This is one of our robots. I talked about how it's modular and you can change it. This is one of the ways that I changed it. It's kind of fun, and it's also kind of broken, so it's not going to go up all the way. But we can dream. So talking to things. How did that happen? I actually forgot to prepare for that too. So the reason why I was on my phone is I was connecting to it. So there's a few ways to connect to things and talk to things. The first of which is Wi-Fi, which we all use pretty regularly. Arduinos can do this, and they can do it really well. So can Raspberry Pis. But when you talk about controlling robots and like at this lower level, Wi-Fi is really hard, but it's definitely the cheapest. Like there are really cheap chips, which is insane. I recommend the ESP 8266. I expect you all to memorize that. I'm going to quiz you at the end. Yeah, Wi-Fi it's all right. Bluetooth is the way that I would go. That's how I did that. So there's like a little Bluetooth module, super cheap. That handles all of the connection. I didn't have to do any of the math. I've got an app that I just put some buttons on and let me do that. And then there's also RF, or radio frequency. So like when you see drones or when you see like those old RC cars, that's what they're doing. Basically, everything you see here is a wave. Everything is like sent in waves. All of the data that we know and love is waves at some point. What's different is like the length of these waves. It's really crazy, but like you can achieve the same thing with all of these. This is the easiest way to get started. Actually, no, this is the easiest way to get started. Really plug and play. Next easiest, but you do have to make an app or have an app to control it. And this is the hardest but most capable. Okay, so what if you're not making a robot or a physical thing? It just exists in software. You don't have to code to prototype it or to get to your MVP. In fact, very rarely do you, unless you're doing some kind of high-level stuff. So if you're making an app or a web thing, I would suggest making mockups. And there's tools and platforms. I like to use proto.io. It lets you make like something that's responsive and like you can actually move it like an app without having to code it. For making a website, I would suggest using Wix or Squarespace or any of those. I've been using Wix for a while. Like I founded a few companies. We all use Wix. Like it's just quick and easy. You can do payments, you can do forums, anything you need. Eventually, you can convert to something higher end, but there's often not a point. So AI and chatbots. You hear a lot about AI, and this is like a super cool area. It's overhyped at the moment. That'll change soon enough. But if you want to make a prototype that does something with AI or chatbots, use a person as your MVP. The dream AI. Like if I could make any AI right now, it would be a person. Like you are smarter than any AI that we will create within our lifetimes, maybe, hopefully. Like as soon as we create something as smart as us, we're in some like really, really weird space. Things might go wrong really quick. But for now, you're smarter than anything any computer can do. So use that and like pretend to be your ideal application. Test that with customers. They don't even have to know that you're faking it, right? Like you could be texting them. You could tell them that it's an AI texting them on the other end. Really easy ways to spoof this, but the end effect is the same. Outputs. So I've gained a perception of the world around me. I've made a decision around what I want to do and how I want to interface with it, and it's time to interface. There's a few ways to do it. There's like light, sound, all that stuff, but right now let's focus on physical things. So let's talk about motors. This is this robot. It's digging here. So it's using what's called DC motors. DC motors is just metal wrapped around other metal, put inside a metal thing. And you apply current and voltage, and it happens to turn. And like how much it turns and how fast it turns is up to a lot of variables. But yeah, DC motors are pretty simple. They're really not bad. Like they're pretty powerful, and they're really cheap too. I use them on most of the robots I use, with some exceptions. So yeah, like I said, all of these use DC. These actuators you see that are lifting it up, that's using a small DC motor and like a linear rod. Some things to know with DC motors, they're happier when they're spinning fast. Doesn't sound like a problem initially, but most things don't need to spin fast. So like this drum, this is as fast as I'd ever want it to go, but no motor spins that fast. So the motor that's turning this spins 13,000 revolutions per minute when it's not loaded. So you have to use gearing to get it down to this, and that adds in a lot of mechanical complications. It just gets tough. Other motors, so stepper motors. This is a little robot I made, and what it's doing is it's looking for an RFID tag underneath the floor, and then it's turning a very precise angle once it sees it. Stepper motors work very differently than DC motors. They're just really precise, so it's like, here's one right here. This is kind of a beefy one. Just pass that around if you want. It's what's used in like 3D printers, CNCs, because it's easy to be accurate with. And then there's servos, so you can't really see it, but there's a servo right here that's waving back and forth. What's cool about servos is it's a DC motor, but you can tell the position. That's one thing I forgot to mention. The reason why DC motors are hard to use sometimes is because you don't inherently know position. All you know is how much power you're applying to it. And there's only 3 ways to control it. You either apply power, you don't apply power, or you reverse the power. That's all you can do. And how fast it goes depends on how fast you turn that on or off. Servos are a little bit different. I just tell a servo, hey, go to this position, and it does. And that's really nice and makes it a lot easier. So yeah, to recap, this is just for you later. Looking at it. Are there any questions about any of these? Okay. So manufacturing. You will never have to make one of these. This is a PCB for like any of your MVPs, right? So when I say manufacturing, I'm talking about manufacturing your MVP. There's a few ways to do this, really 2. Additive manufacturing and subtractive. So additive manufacturing is 3D printing. Very common. I love 3D printing. All of our robots are 3D printed. This is useful in places where you've got kind of a complex part, but it's like relatively small. And it's also like not going to withstand that much force. So like I've got 3D prints. Let's see. So like here's our wheel. Like I can put this on the ground and stand on it, and it like moves the motor hub, but the part doesn't break. Like, they're pretty strong in certain applications. You should not use them on super big parts because super big printers are super expensive and things that support a lot of weight. They also melt at high temperatures. So like I've left robots in the car that are 3D printed and then they melt. It's really sad. Just get it, it falls apart in your hand. So to do this, actually I'll get into this in a second about how to do it. There's also subtractive manufacturing. So with 3D printing, I'm like depositing plastic layer by layer. It's called fused deposition modeling printing, which is what I was showing there. So I'm just putting things layer by layer. I'm building up what I want. With subtractive manufacturing, I start with something. So like you start with a big piece of wood, and then you cut away the parts you don't want. It's kind of like poetic in a sense, because the thing that you wanted was already there. It was always there. You just had to take away the things that you didn't want. And you should use this for things that are like large, flat, structural. You can do like really cool engraved signs. Don't use it for things that are complex in 3 dimensions. So how to do these things? Step 1, you make a 3D thing. And making a 3D thing is just using simple geometries like squares, circles to make your thing. And you use a CAD program called OnShape for that. Once you've made your 3D thing, you use a program to tell the machine how to make your 3D thing. This is called a slicer. It's cutting this cute little boat into a bunch of tiny little layers. And when the 3D printer makes this, it just goes layer by layer and makes it in the opposite direction this is going. So that produces what's called G-code. And the G-code is kind of like a 3D printer or a CNC's instructions to follow. After you've done that, you make the machine make your thing. This is the easiest part. It's usually just hitting a button, selecting the file. It really is just 3 steps. How to do those things, you've got to learn those specific programs, but like, there's not a lot going on. If you don't want to use those, which you really don't have to, these are the ways that I would make things like quick and dirty. Cardboard, love this stuff. It's amazing. You can make a lot of things with cardboard really quickly. You can also use PVC pipes. These are really fun. I like to heat up PVC pipes, so for a while I would like make robots out of that. So you like heat it up and bend it, and it's pretty cool. It also releases like poisonous gas. Don't do it in a closed room. Wood, also useful. You can like cut it, drill it, machine it, sand it, lots of things. So yeah, now we're at the last step. We're going to make our thing. Just start. Just do it. It sounds like a jerk instruction, but like really, this is kind of a hard part. Like you've thought about it for a little bit. Now you actually have to like take the leap and try it. And this is where you're putting yourself out there to fail, which is okay. Like so many things I've made sucked and didn't work. That thing broke when I tried to winch the spider back up. Like it just happens. So just started making it. Really doesn't have to be perfect. Just make something. And then don't be afraid to ask for help. So I am a resource that you can use through the studio. Like my email's on this slide, and I'll email you the slide so you'll have it. Like you can reach out to me, and I'll help you with any project that you have. I love doing this stuff. Other resources, McMillan Innovation Studio. We'll have a makerspace very soon, hopefully by the end of the month, set up and running. 3D printer, CNC mill, anything I mentioned here you can do there, and I can help you with. The Fab Lab, which is right next door, they've got all this stuff, but you do have to pay a membership fee, so yeah. The engineering college has some resources. this can be like hit or miss because like the engineering students need that stuff sometimes, so it's like getting it when they don't. But if you know somebody who's like a student, they could probably slip something in for you if you need. When it comes to making something, the key is like what you make is not the final version. It doesn't have to be, right? You can improve upon it. And that's probably the most important step. Like, this telephone is great, not because Alexander Bell made this. The telephone he made, by our standards, sucks. Like, really badly. Innovation is taking ideas and improving upon them. It does not mean, like, something has to be great from the start. Like, I can't get this across enough. Like, the first thing you make does not have to be great. It's the continued innovation, the continued saying, what's wrong with this, how can I make it better? That's what makes things great. That's why our world is so enabled by tech, because you have so many people saying, how can I make this better? The same thing happens, and should happen, with the things that you make. So when you make it, you want to test and evaluate it. You want to see, does this meet your constraints? Can this pick up dirt? Like, very at the core, just test those. And those are pretty easy to tell right away. Try to avoid bias with your design. When you make something, it's like your baby. It's like a part of you, in my mind. And so it's really hard to get feedback sometimes. Just like take yourself away from that and think of it as like when people give you feedback, they're just trying to make it better. And then try to isolate variables and test for specific things if you can. And then you iterate. It all starts over again. Everything you saw there, more or less. Like, iteration is basically innovation. And you want to do this as much as you can with as much time as you have. So that in mind, let's try a thing, a challenge, and apply this. So you have a 2x2 by 2 box, 2 foot. And you come across a creek. I don't know why you have the box. I don't know why there's a creek or you're in the woods. But you are. And all you have is like string in this box. And you want to get it across this creek. And let's say this creek is like from this line, I guess you can't see it, to all the way over here. So you can't really jump it. Not very easy to get across. But you need to get it across. You need to get yourself, well, no, you don't need to get yourself across. Anyways, you can use materials on the wood. Don't worry about tools. If you need a tool, you've got it. But you can only use what you can find around you reasonably. So what I need you to do is to get into groups. I guess you're already in groups. That's cool. And then we're going to hand out some paper. And I'm going to put a timer up there. You get 10 minutes. You want to generate 5 designs. And then you want to narrow that down. Narrow that down to like 1 or 2 designs. Then have an idea for how you make it. And then when that 10 minutes is up, somebody from your group will talk about your designs and why you chose what you chose. Sound good? Any questions? No? All right, cool. You're standing. All right. Do we have paper? Yeah. Does everybody have pens? I don't have pens. No? Okay. Well, fine. I guess everybody gets paper.
How good. You don't want to tell us what things are.
Do like a slack water motion. 2 trees. Tie 2 trees. Pull around. So does it say if you're allowed to go across? I guess. Someone's
You made us so scary.
it wasn't very smart. We're just trying 5 and we use like hopefully
The question is, you're on one side. I'm on one side. How do you get to the other side?
Oh, I forgot to add one thing. You're trying to like make your thing and like get it done as soon as possible. Like there's a bear chasing and you're like, I gotta get across this. Like really quickly, as quickly as you can. So use that as a constraint.
So when we make
There's also snacks and drinks in here if you want anything. Please do. Try and throw away.
I care a lot less about the bonds.
I'm gonna go ahead and just draw my idea here just so we have some.
Marks the holds key there in the package keys like shoulder. It's like something.
This does require a use cross.
And then like secures around the line.
Yeah, we just.
Use it or shove it on its head.
Is it like what is it? Is it a raging river? Oh, it's just a key. Oh, you can use it. So can we just walk through it?
Let's pretend it's like your turn.
So we just drops to about 70 feet.
You can use it.
It doesn't say that.
It doesn't say.
You know, that
One way.
walks across the creeks around the world.
Yeah, okay. One. Swing the.
I like the lasso.
All we need is 5 I can't draw either. So here's the ring.
None of us can finish.
Hey, we have any tool we want.
Yeah, I gotta see him. Sixth grade, so that's a good one. Is that good enough?
I have a build a bridge. Another layer. Have 2 logs together.
It just says you can't get wet. It never says how much you're supposed to have.
Next one is you tie it through.
Yeah, so it's just like
The rope from one tree to another.
The strings that you tie it.
Kind of similar. The rope is. I don't know if we can get across before we like leave it there. Because the rope is really like the tree is like that. It's really getting across tight. Right?
oh, like you're right.
Okay.
Can slide across 2 logs or 2 sticks and just lay down, grab that channel, the creek's flowing. If you get those sticks that are stuff that you can get like a small structure, it's like a reverse sail. Yeah, it'll float. So the ability to slide down across the stream. Next off, yeah, bridge. Yeah, it was you can also use have tree.
No, I just it was kind of like a
Oh, I got it.
Small, raft.
yeah, bro. What you talking about, you guys?
Dude, I did. Well, I guess you know I think a concept or something, man. Because you guys okay.
Yeah. So that is the I'm assuming that there's slightly broken. By the way, I got jump across the garage.
So we would like to tie our strings.
So we can like swim it.
We could,
So it's the other really stuff still. This is where
And then we can throw the boxes.
If there's bamboo, just like grab a few sticks of bamboo. Yeah, the other ones you just like stretch it.
It doesn't have to be like a perfect stone, just enough to like move you away.
We're assuming that we're not told it's
They ask what kind of.
There you go.
They ask how big the rock is.
yeah, vines.
I'm Charles. Charles? Yeah. Nice to meet you. Oh, but we couldn't do the things like some of these. Because like enough of these. Most of these, of course. We can do it.
Yeah.
Because if you get enough leaves,
It's not that big of a
yeah, it's not that big of stuff. They're like enough leaves, you know, a little thing. I'm trying to figure out. I'm trying to figure out. That was my first song. We just can't.
Oh my god, it's a spider! I like that idea. You kind of like catapult a tree branch.
Oh, I like that idea.
And people were like cheering. You got 50 seconds. Yeah, this wasn't nice. This one was something nice. I came in shock. 30 seconds.
Also, supposed to quickly drop. You were supposed to reel it down.
Yeah, I would.
Yeah, well, we split our time. Half time was okay. Like a casual kind of small percentage.
Yeah, 9 seconds to think of that.
And the other half was village. Ate some good stuff. Monkey liver. Did you see the monkey before?
I'm just gonna leave this on for the rest of it. Is that? Right. Let's go ahead and share the things we came up with. You guys want to share like your top design? And what I'm curious to see is like, is their design convergent? So like, did everybody think the same thing, or is it like unique? So, you guys want to start us off?
Yeah. Do you just want us to share like our top? All right. We're gonna put it to our top two.
Yeah, that's fine. If it's quick, you can do it.
All right. So what we did is we took the string. We tied one end of the string to a stick, right, like a pretty big stick, and then we tied the other end. We wrapped it around the box. So then what you could do is you could take this string, as long as you have enough of it, you could throw it into like a tree branch on the other side of the creek, and then you could just lift it up and swing it across like a pendulum. Our other one, you just kind of tie it to the end of a really big stick, like a fishing pole, and just reach across. Thank you.
Cool. You guys want to go?
Sure. I guess the one we kind of ended on was fashioning a very small, my drawing won't make any sense, very small raft with just a box to float on, and you can either take the string and like, tie it to the raft and get across yourself, because you can more allowed to get wet, and then you just pull it as it floats, you can just pull it to you, and then you can get it to go. That was our top idea.
Alright, that's it.
Okay, I guess. Well, the design we did, I think, is
side of the creek, and then punch a hole through the box, and then basically just zip line the box to the other side.
So we pretty much had their same idea in a sense, except we didn't like tie it to a stick, we just tied it to a tree and then swung it across. And then we also had one where we tied like some string from one side of the river, like to a tree to another tree, and then just like slid it across.
Well, we had a couple ideas. First, we decided to go ahead and carry the box just across the
You win, guys. That was the win.
Like, yes. Okay, and then we had an idea to catapult the thing from a tree branch. And another idea was to maybe put some shrub, kind of like enough shrub, and then put the box on top of it, try to like float it across. And yeah, those are our ideas.
Nice.
Well, we had a few more ideas, but I guess you guys heard them and took them. So we're gonna build a raft, and we're just gonna like let it float.
Nice.
To the other side of the creek.
All right.
Yep.
And then, do you have one? Joe.
First one was just to throw it. And the other ones were just kind of the same, but like build a small raft, attach the string to the string, put a rock at the end, throw the rock to the other side, and then put the box on the raft so to make sure that it goes down the other side instead of just going down straight.
Nice. Did you have some? Yeah. Okay. All right. Is that everybody? Okay. Cool. So the key takeaway from this is, well, there really isn't one. I didn't have that much foresight, but it was fun, right? No, okay. So like, there's so many ways to approach a problem. I mean, there was like some overlap, but just about everybody had a slightly different approach and variance. So, like, talk to other people when you're making things and get feedback on it. And then just try it. Like, a lot of those were like really simple to try. Like it's really easy just to throw the box. And I know this is a very like simple and weird and probably poorly constrained example, but like when you start to look at other problems you go to solve, just write out what you could do and then start narrowing down what works and what doesn't, right? You could pretty quickly narrow down, oh, this is too heavy for me to carry. You could pretty quickly narrow down, oh, the wood that I have around me can't float. So that throws out anything that can float. So when you approach a design thing, you want as many things as possible, and you want to find like similarities in those, and you want to just narrow it down and down, make it a little bit better, and eventually you can get the box across and not get eaten by a bear, and that's a good day for everybody. Anyways, thank you all for coming. I really appreciate it. Again, I'm here as a resource, and I'm going to email these. Have a great fall break.